giant machine just for smashing tiny things together.
Right, that's the popular image, smashing protons.
Exactly. But have you ever stopped to consider that it's also, well, a powerful creator?
Ah, that's a great way to put it.
These high-energy collisions, they actually birth new particles. It really makes you wonder, where on Earth do they actually come from?
That's the really fascinating question we want to get into today. We're going to do a deep dive into this seemingly almost alchemical process happening right inside the LHC.
Alchemy, yeah, like turning lead into gold. But here, it's energy into matter.
Precisely. How pure energy can transform into the very stuff that makes up, well, everything, matter itself.
Okay. And we've got some really good material that gets right into the heart of this energy to matter conversion business at CERN.
Mm-hmm.
So our mission for you listening is to try and make sense of this incredible phenomenon. We want to unpack the surprising science behind it and maybe explore why this connection between energy and matter is just so important.
Sounds good. And I think the best place to start, the foundation really, is probably Einstein's most famous equation. EMC
Well,
equal.
right, E equals MC squared. Everyone knows it or has seen it at least. But what's the real takeaway when we're talking about creating particles inside a collider?
Well, the core idea, the absolute bedrock, is that energy and mass aren't really separate things.
Okay.
They are fundamentally two different forms, maybe manifestations, of the same underlying thing. A bit like water and ice. Same stuff, different state.
Ah, I see. So they can convert into one another.
Exactly. Einstein's special relativity showed this deep, deep equivalence.
And that c squared part, the speed of light times itself, that's the conversion factor, right?
Yeah.
And it's huge.
It's absolutely enormous. I mean, T-speed's about 300 million meters per second. Square that, and you get roughly 9 times 10 to the 16th. 9 times 10 16.
Whoa.
So that massive number tells you that even a tiny, tiny amount of mass contains or is equivalent to a staggering amount of energy. And conversely, to create even a very light particle, you need to pack in a significant amount of energy first. It just shows the incredible energy density locked within matter.
That's hard to wrap your head around. So even like a speck of dust has this immense potential energy.
In theory, yes. The energy equivalent is vast. Actually, extracting it is a whole different challenge, of course.
Right. Practicalities.
But the principle holds.
Yeah.
And to actually see this energy morphing into new particles, in a controlled way, you need some pretty extreme conditions.
And that's where the LHC comes in.
That's exactly where the LHC comes in.
This giant 27-kilometer ring deep underground, how does its design actually make this energy to matter thing happen?
Well, it's basically the most powerful particle accelerator ever built. It takes particles, usually protons, or sometimes heavier things like lead ions, and gets them going incredibly fast in opposite directions.
How fast are we talking?
We're talking speeds exceeding 99.9999% of the speed of light, so really close to the absolute speed limit of the universe.
Wow, okay. How do they even do that?
It involves thousands of powerful superconducting magnets to steer the beams around the ring, and then these things called radio frequency cavities. They give the particles repeated kicks of energy.
Like pushing a swing.
Sort of, yeah. Pushing them higher and higher in energy terms, surfing an electromagnetic wave, essentially.
Okay, so they're whizzing around near light speed.
Yeah.
What happens to their energy?
That's the key. As they get faster and faster closer to C, their kinetic energy, the energy of their motion, just skyrockets. It becomes vastly greater than their rest mass energy, the MC of P part, when they're just sitting still.
So it's the movement, the sheer speed that provides the energy for creating new stuff.
Precisely. It's this huge amount of kinetic energy that gets unleashed when these beams collide head-on inside the giant detectors.
Detectors like ATLA or CMS, those huge experiments.
Exactly. And the total collision energy can reach up to 13.6 tera-electron volts. 13.6 TeV.
TeV? How much energy is that, really?
Well, it sounds technical, but picture this. It's roughly the kinetic energy of a flying mosquito.
Okay. That doesn't sound like much.
But here's the thing. That energy is concentrated into a space about 1 trillion times smaller than the mosquito.
Oh. Okay, right. That changes things. So you have these incredibly energetic points smashing together. What happens right at that moment of impact?
For an almost unbelievably short time, we're talking something like 10 to the minus 25 seconds.
10-25 seconds.
That's unimaginably fast.
It really is. In that instant, all that kinetic energy is released and concentrated into a minuscule volume, smaller than a proton. This creates an energy density that's just astronomical, way beyond anything else we can create.
Like focusing lightning onto the head of a pin, but much, much more extreme.
A good analogy, yeah. And it's this tiny, super energetic point where the magic, or rather the physics, happen.
So how does that intense energy actually become particles? Does it just pop into existence?
This is where we need to bring in quantum field theory, or QFT. It's our best framework for understanding fundamental particles.
Okay, QFT. So particles aren't little balls. Not really, no. In QFT, particles are seen as excitations like ripples or vibrations in underlying quantum fields that permeate all of spacetime. Think of an invisible ocean filling everything.
An ocean. Okay.
And the intense energy concentration from the collision basically stirs up or excites these quantum fields.
So the energy disturbance is the particle, or creates it.
Creates it is probably the better way to think about it. If the energy available in that tiny region, the E from the collision, is greater than or equal to the rest mass energy, the MCI, needed to make a certain particle.
And it's antiparticle, usually.
And usually it's antiparticle, yes, we'll get to why in a moment.
Yeah.
Then that particle pair can effectively condense or pop out from that concentrated energy. It emerges from the vacuum, fueled by the collision energy.
That is EMC happening right there. Energy converting directly into mass.
That's it, in action. The kinetic energy is transformed into the rest mass energy of new particles.
It still sounds a bit like magic, pulling particles out of energetic thin air, but I assume there are rules. You can't just make anything.
Oh, absolutely. Very strict rules. This isn't random chaos. It's governed by fundamental conservation laws. Physics has very strict accounting.
Okay, like what?
Well, the big ones are conservation of energy and momentum. The total energy you start with the kinetic energy of the incoming particles plus their rest mass energy has to exactly equal the total energy of all the outgoing particles, their kinetic energy, plus their rest mass energies. Same for momentum.
Makes sense. Energy in equals energy out, momentum in equals momentum out, no free lunches.
Precisely. Another absolutely crucial one is conservation of electric charge.
Ah, so positive and negative charge.
Exactly. The total net charge before the collision, which is often zero if you collide a particle and it's antiparticle, or just 2 protons, must be the same as the total net charge of all the particles created afterwards.
And that's why you often get particle-antiparticle pairs, like an electron and a positron.
That's a major reason, yes. An electron has negative charge, it's antiparticle. The positron has positive charge. Create them together, the net charge created is zero. It balances the books.
Clever. Are there other conservation laws like that? You mentioned baryon and lepton numbers earlier.
Yes, those are important too. They're quantum numbers that basically keep track of different families of particles. Baryon number tracks quarks, the things inside protons and neutrons. Lepton number tracks electrons, muons, tau, and neutrinos.
So you need to make sure you end up with the same net number of quarks and leptons, in a sense.
Essentially, yes.
Yeah.
These numbers must also be conserved. And again, creating a particle-antiparticle pair is a great way to do that because the antiparticle has the opposite baryon or lepton number, so the pair together adds 0 to the total count.
So conservation laws, energy, momentum, charge, these family numbers, they really dictate what can be created.
They constrain the possibilities significantly, yes. They guide the transformation of energy into specific types of matter and antimatter.
Okay, so given that energy from the collision and these strict rules, what kind of particles actually do get created? What's in this particle zoo?
It's an incredibly diverse zoo, thanks to the high energies. We can produce pretty much all the fundamental particles described by our current best theory, the standard model of particle physics.
The standard model, right. What does that include?
It includes the 6 flavors of quarks, the up-down, charm, strange top and bottom quarks.
The building blocks of protons and neutrons.
Exactly. And then there are the leptons, the electron, the muon, the tau, which are like heavier cousins of the electron, and their associated neutrinos. 3 types of neutrinos.
That's a lot already. And what about the forces between them?
Good point. The particles that carry the fundamental forces, the gauge bosons, are also produced. You get photons, the carriers of electromagnetism.
Light particles.
Right. You get W and Z bosons, which mediate the weak nuclear force responsible for certain types of radioactivity. And you get gluons, the carriers of the strong nuclear force that binds quarks together.
Gluons, like glue.
Exactly. And of course, the star particle discovered at the LHC itself in 2012, the Higgs boson.
Ah, the Higgs. The one associated with giving particles mass.
That's the one. Its discovery was a huge confirmation of the standard model, and it's created directly from the collision energy via EMC fornex.
And antimatter. You mentioned positrons. Is there an antiparticle for everything?
Pretty much, yes. For every quark, there's an antiquark. For every lepton, antilepton like the positron. Same mass, but opposite charge and other quantum numbers. So the LHC is also a significant antimatter factor.
We're creating bits of antimatter right here on Earth.
We are indeed. Fleetingly, but yes.
And you mentioned quarks and gluons. Do they just fly off on their own?
Not usually. Quarks and gluons have a property related to the strong force, sometimes called color charge, which means they can't exist freely on their own for very long. It's called confinement.
So they're stuck together.
Basically, yes. As soon as quarks and antiquarks are created in the collision, the strong force very quickly pulls them together, almost instantaneously, to form composite particles called hadrons.
Hadrons, like the H in LHC.
Exactly. Large Hadron Collider. These hadrons come in two main types. Mesons, which are made of one quark and one antiquark, and baryons, which are made of three quarks.
Because protons and neutrons are baryons.
Protons, two ups and a down quark, and neutrons, one up and two down quarks, are the most familiar baryons, yes. So the LHC creates lots of protons, antiprotons, neutrons, and many other more exotic, unstable hadrons too.
So it's a whole cascade. Energy makes fundamental quarks and leptons and bosons, then the quarks quickly bundle up into hadrons.
That's a very good picture of it, yes. A spray of particles emerges from the collision point, which the detectors then track.
And the really exciting part, I guess, is the potential to create things we haven't seen before, stuff beyond the standard model.
That is absolutely the holy grail for particle physicists today. The standard model is great, but we know it's incomplete. It doesn't explain dark matter, for instance, or dark energy.
Right, the big cosmic mysteries.
So many theories propose new, heavier particles that could solve these mysteries. Think theories like supersymmetry or extra dimensions. If these new particles exist, and if their mass, times c squared, is within the energy reach of the LHC,
then MC says we should be able to create them in the collisions.
Exactly. The energy could convert into these new, undiscovered forms of matter. That's what researchers are constantly searching for in the LHC data, unexpected bumps or signals that could indicate new physics.
That's incredible, finding entirely new building blocks of reality. So, stepping back a bit, why does this whole process energy becoming matter in the LHC, why is it so fundamentally important? What does it tell us about the universe?
Well, in several really key ways. Firstly, is like having a time machine, in a sense.
A time machine, how so?
The energy densities created in LHC collisions are so high, they mimic the conditions that existed in the entire universe just fractions of a second after the Big Bang.
Whoa, so we're recreating the early universe.
In tiny localized spots, yes. Back then, the universe was this incredibly hot, dense soup of energy and fundamental particles popping in and out of existence. The LHC allows us to experimentally probe that era, to study the kind of particles, especially heavy, unstable ones, that were common then but aren't around naturally today.
So we get a direct look at the universe's infancy, testing our ideas about the Big Bang.
Precisely. Secondly, by creating all these known standard model particles and measuring their properties, their mass, how they interact, how they decay with extreme precision, we put the standard model itself through incredibly rigorous tests.
Looking for cracks in the theory.
Exactly. If we measure something that deviates even slightly from the standard model's predictions, it could be a huge clue pointing towards new physics, new particles, or new forces we don't know about yet.
And that ties into the search for things like dark matter.
Absolutely. The LHC is one of our primary tools in the hunt for dark matter. If dark matter particles can be produced in high-energy collisions, even if they escape the detector without being directly seen, they might leave behind a signature, like missing energy or momentum, that we can detect.
So it's probing the known, looking for the unknown, and recreating the past all at once.
You've got it. It's a multi-pronged attack on the fundamental mysteries of matter, energy, space, and time.
Okay, so just to sort of wrap this up then. The Large Hadron Collider isn't just smashing things apart, it's fundamentally an engine of creation. It takes the incredible kinetic energy of particles moving near light speed and uses it, via EMCF4, to literally create the mass of new fundamental particles, both known and potentially unknown.
That's a perfect summary. It's this direct, dramatic demonstration of the equivalence of energy and mass happening thousands of times per second inside the machine.
It's an amazing feat of science and engineering, really, recreating those primordial universe conditions in a lab here on Earth to figure out what everything is ultimately made of.
It really is quite extraordinary when you think about it. We're probing the very fabric of reality.
And it leaves you with this really profound thought. Every single particle that makes up you, me, the studio, the planet, everything, ultimately started as pure energy in the Big Bang.
Yeah.
This deep connection, this interchangeability between energy and matter, revealed by physics and demonstrated right there at the LHC, it's fundamental. Makes you wonder, doesn't it? What other secrets are still locked away inside that simple, elegant equation, EMC Kino, just waiting for us to find the key?
That's the question that keeps physicists going.
Yeah.
What else is out there?